Okay, so we're going to continue on. So the point we've got to at the moment is we've divided up, in fact I'll turn it back over and I'll show you what we've done. We have divided up our rectangle into 4 little rectangles. We've said that the contour integral around the large rectangle must equal the contour integral around each one of these rectangles added together, and each of these is an arbitrary complex number. We've then said that one of them, at least one of them, must have a modulus such that it is greater than or equal to a quarter of the modulus of the larger one. And now what are we going to do? We're going to do basically an iterative process. We're going to pick whichever one of those rectangles satisfies this condition. So it could be this one, it could be this one, it could be this one, it could be this one. More of them could than one of them could satisfy that condition. In fact, all of them could have a modulus greater than this one, and they just happen to be in such silly opposite directions that they all cancel. But at least one of them will be. So just pick, if more than one of them satisfies this condition, then just pick one of them. What we've proven is that at least one of them must satisfy that condition. Okay, so I can always find a rectangle such that this is true. So pick that one and call that R1. So we've abandoned all the others, we've chucked them away, and we're now taking whichever one satisfies that equation, and we are calling that our final R1. So at the moment we've got R0 and we've got R1, and what we know is that R1 is contained within R0. Now what we're going to do is do the same thing again. So we go to our rectangle R1, which could be any one of these 4, and well, whichever one satisfies this condition, providing it satisfies that condition. And we do the same thing. So let's suppose it's this one that has satisfied that condition. Then we'll divide that up into 4 pieces in exactly the same way. And for the exact same reasons, one of these, at least one of these, well, for the exact same reasons, if you add up all of the contour integrals around this one, this one, this one, this one, it will give you the contour integral around the larger one. So we can then do the same argument again. We can say at least one of these 4 must have a. So if we call these R21, R22, and I'll just put in the etas plus and the eta. And R1 must equal this, plus eta R32 plus eta, oh, you can't see this, eta R42. Basically, I've just written out that if we've divided this into R21, R22, R23, R24, and then the contour integral around R1, that should say, is equal to the contour integrals around all of them. And for the exact same reasons, the modulus of the contour integral of eta R1, so we know, I'll go over to the next page, we know now that the modulus, the modulus of the contour integral around the rectangle R1 must, well, we can find one of the R2s such that the modulus of the contour integral around the rectangle R2, where I is some element, well, I is between 1 and 4, and it's an integer, a natural number even. So once again, we can pick a rectangle, basically, one of these 4 smaller rectangles within R1, and we can pick it such that its modulus is greater than or equal to a quarter of this one. But we know that we picked R1 such that its modulus was greater than or equal to a quarter of the modulus of the contour integral around R. So now, by the whatever property that is called in total orderings, oh goodness, can I remember back to numbers and sets? It might be called transitivity. I think it might be called transitivity actually. Yes, it's certainly a transitive relationship, but whether it's called transitivity in the lingo of totally ordered sets, but by the property that we've known for years, if this one is greater than or equal to this one, and this one is greater than or equal to this one, then it implies that this one is greater than or equal to this one. Well, no, sorry, you have to obviously keep the quarter, because what we'll have to do is we'll multiply it by a positive number, which we can do by the axioms of totally ordered sets, and the relationship still holds true, so we get 4 squared there, and then we say that because this one is less than or equal to this one, and this one is greater than or equal to this one, it implies that this one is greater than or equal to this one. So we therefore get that eta R2, R2I at the moment, is greater than or equal to 1 over 4 squared eta R. Oh no, what have I done? Okay, so whichever rectangle that was, we call that R2. And we've now got a sequence of R0 contained in R1, contained in R2, such that R1, the modulus of the contour integral around R1 is greater than or equal to a quarter of the modulus of the contour integral around R, and this relationship for R2. And we can keep going. We can get an R3, which is contained within R4. Oh no, not like that. What have I done? No, these are all the wrong way around. Sorry, R0 and R1 is contained within that. R2 is contained within that. R3 is contained in with that. We can get a sequence, basically, of nested rectangles. Okay, and they all satisfy the property that Ri, if we take some element on this sequence and we take the contour integral around it, well, it's going to be greater than or equal to 1 over 4I eta R. I don't feel like I've oh no, this should say the modulus. I don't feel like I've done a particularly brilliant job of explaining that, but I don't really know how I can improve what I can do to save it now. So we're just going to move on. So I'm now going to pull the wool over your eyes, basically, because there's a horrendous theorem from topology that says that basically the intersection of count of the infinite, sequence of nested regions is non-empty. Oh, and we need that to go on. We need that. Basically, that as we know, of course, that the rectangle Ri is not going to be empty, but we want this sequence of nested intervals to converge to a point, and for that we need the intersection of them to be non-empty, and the point that's in the intersection of them is going to be the point that they converge to. And I think I'm going to have to end this video